So broadly speaking, I won't bother reading my outline to you, but basically I'm going to focus on the chemistry of uranium, since I feel like most of us learn a little bit about how nuclear fission operates in high school, if nothing else. But the actual chemistry that makes uranium do what it does in the environment is a little bit less well known. So I'm going to try to focus on that before we try to at least wrap things up and have at least a little bit of a discussion about the significance of this for society. What use should we make of the nuclear materials we already have and could potentially mine? So uranium is different. That's what attracted me to work on it in graduate school in the first place. So if you're living in most of the periodic table, let's take chromium as a good example. What does chromium do in minerals? Well, it can be trivalent chromium, for example, which means that it will draw oxide anions around it in a fairly loose coordination, polyhedron, probably 6 oxygen anions. And that polyhedron will change from mineral to mineral or in aqueous solution. Chromium-6 will draw 4 oxides around it in a very tight tetrahedron, and that will be a somewhat durable complex anion, just like sulfate or phosphate or the other things we learn about in hopefully high school chemistry. Uranium, on the other hand, does things just a little bit differently. So let's talk about what that means. So it's got 2 common oxidation states in the environment. One is uranium-4, and uranium-4 is fairly typical. So it's the Dr. Jekyll of the 2 oxidation states. So it will draw a number. It's a large cation, so it will draw a number of oxides around it to form a coordination polyhedron, and that will behave more or less like zirconium or thorium or a number of other fairly common. They're still trace elements, but they behave in the ordinary fashion. These polyhedra are sort of fungible. You can bring oxygens in, push oxygens out fairly easily. Uranium-4 compounds are typically black. This is uraninite, which is just uranium dioxide. This is quartz with coffinite in it, which is uranium silicate. It has the identical crystal structure to zirconium, so I've placed the zirconium crystal structure here because they're easier to come by, but it's the same thing. This is uranium instead of zircon or zirconium in the green polyhedra with silicon in the blue tetrahedra. And these uranium-4 minerals are pretty insoluble. Uranium-6, which is what you get and Brother Guy is not here. Brother Guy has a great moment in his planetary science textbook where he asks you to consider what type of exoplanet would most likely have life, is the one with the most ridiculous caustic gas in the atmosphere possible. So you may not have noticed, but we have 20% free oxygen in this atmosphere. Stuff catches on fire on this planet. That's weird. Way out of thermodynamic equilibrium. So in that really ridiculous caustic environment that has been created for us, uranium will oxidize all the way up to the 6+ oxidation state, and that's the Mr. Hyde. That's the weird one. So what this will do, instead of drawing 4, say, which is the most common number of ligands around it, it will just draw 2, form this linear complex cation, which nothing else on the periodic table does other than uranium and some of its friends down there at the bottom row in the actinides. So this produces weirdness, basically. In solution, it might gather, say, 5, also 6, occasionally 4 ligands around it to form pentagonal bipyramids, hexagonal bipyramids, or occasionally squarish bipyramids. And uranyl compounds tend to be bright yellow colored, unless there's something else also coordinated with them to change the color a little bit. So some more examples of what this looks like. So here's a rod model of a uranyl acetate complex ion. So you can see that 6 oxygens from the acetates have coordinated in more or less the equatorial plane of this uranyl ion. So that's what happens when uranyl forms minerals, when it forms aqueous complexes. That's the type of geometry you're talking about. Over here, I'm going to draw your attention to this. Here's a complex carbonate ion. So this is where the weirdness of the geometry starts to have practical effects. Carbonate dissolves, it complexes and encourages uranium to go into solution. Nothing else does that. You add carbonate to a solution, if it's going to precipitate anything, carbonate will usually precipitate it, not uranium. not uranyl anyway. And just to show some of the weirdness of what else uranium can do in solution, it can actually, so this tendency to bond in the equatorial plane will encourage you to form sheets in particular, sometimes chains. And occasionally a sheet can wrap around on itself and actually form what, for want of a better term, I'm going to call a buckyball. So a uranium peroxide buckyball, and these are actually things that could conceivably form, say, in a spent nuclear fuel repository, because they depend on peroxide, which can be created by radiolysis of water. There's plenty of uranium, and these things are actually kind of stable and could be a dominant form of uranium in solution. Okay, so the upshot of this is that uranium 4+, sparingly soluble, uranium 6+, soluble, and in fact weirdly soluble. So in a sort of ordinary natural groundwater with a little bit of sulfate and a little bit of carbonate in it, you'll expect that under reducing conditions, uranium will precipitate out as uraninite or some other solid uranium-4 phase. And then in aqueous solution, you'll have some strange uranyl carbonate, hydroxide, maybe even sulfate, but that will be floating around in solution. So if you've oxidized things, you tend to immobilize the uranium. And if you don't want the uranium to move, that's bad. So you want to avoid that whenever you can. Okay, so a little bit about the history of uranium exploitation. Everything has a boom. It's a great American story, right? A resource becomes known for one reason or another. People go out, it becomes a cultural phenomenon, just like the 49ers going for gold. There was a brief phase where it was a popular culture phenomenon in the 50s to go prospect for uranium, to get your little Geiger counter, and a pick, because you got to have a pick, right? And to go out and look for uranium. So many small claims were filed, and those claims got sponged up into large conglomerates, and it follows the same story that mining almost always follows. So a couple of representative, there are many different types of uranium deposits, but a few representative types, just to show how the basic chemistry of uranium plays out in the environment to create ore deposits. So this is Cigar Lake up in northern Saskatchewan, a little ways from here if you want to go visit it. It can be attacked by wolves up there. That was one of the things that came up when I was researching this site, was apparently some of the people on guard have been attacked by wolves because they need prey. So the genesis of this deposit is thought to depend on the fact that it has oxidized rock, Phanerozoic rock, a red bed of some kind, on top of a metamorphic, probably Proterozoic rock basement. So this is a metamorphic rock that has graphite in it, which means that it's a reducing environment. So some regional hydrologic phenomenon encouraged water from this formation to well up into the overlying formation, where it met an oxidized fluid that had scavenged some uranium from somewhere. And so at the interface between these fluids, you have and this is actually a world-class, as they say, deposit that's 5% uranium, which is a very, very high-grade deposit. So at this front, and this is a type of deposit that forms in many places around the world for many different types of metals. In this case, it's the redox chemistry governing the fact that the reducing fluid knocks the uranium out of solution at the mixing interface. And there are many deposits like this in Canada and elsewhere. A standard Western US type of deposit that Lucy might have been looking for is called a roll front deposit. And once again, it starts with oxidized groundwater that has picked up uranium from somewhere. And the somewhere might be a granitic basement rock, so say a Proterozoic granite, which would have some amount of uranium in it. Or it could be a recent volcanic rock, like a ashfall deposit, which there are many of in the West. So either one of those could serve, perhaps both of them have served as sources for the uranium. Oxidized, in equilibrium with the atmosphere, groundwater picks up the uranium and it starts to migrate. And if it migrates into a permeable formation that has organic material in it, say something dirty like a delta deposit, an old stream channel deposit, those are the classic host rocks for roll front deposits. So the oxidized liquid migrates into this permeable, organic-rich deposit, and there's a chemical reaction. The organics reduce the uranium to uranium-4+, it precipitates out. As the oxidized fluid continues to migrate in, it consumes this organic matter, and then the uranium moves down to a new front. So there's this rolling front, and it not only, is that thought to be the genesis of it, but of course it sort of looks like that. These red tongues that are drooping at the edges are the roll fronts, and they give their name to the style of deposit. So, okay, so much for a very brief sketch of a couple of types of ore deposit and why uranium does this sort of thing. So the history of uranium mining, and this only goes back to the 60s. There was a boom in the 50s and 60s, which was government driven because we wanted to keep ahead of the Soviets, all that good stuff. Uranium in general is economic at tenths of a weight percent grade. It depends on local conditions. It depends on how hard the uranium is to get out of the rock. It depends on how hard the uranium is to get out of the region. If it's the Congo, the political environment or the infrastructure might not be there to make it very easy to get the uranium where it needs to go in order to be consumed. The era of building nuclear power plants was the late 60s and the 70s. People needed to fill those power plants, so they bought uranium, and there was a market boom in the 70s. That collapsed. 3 Mile Island happened. Chernobyl happened. People decided they wanted to do other things. The price of oil and gas dropped. All of that stuff combined in the 80s to cause the market to crash, and it stayed crashed for quite a while. There was a boom in the aughts due to increasing price of gas, but we figured out how to do shale gas. And then Fukushima happened, and the price cratered again. We may be seeing the beginnings of another rally, it's hard to say. So once you've located your uranium deposit, how do you get it out of the ground? Broadly speaking, you could mine it conventionally, or you could do something a little bit more sophisticated. So conventional mining breaks down into underground mining, where you sink a shaft to where the richest stuff is, and you mine that richest stuff. You bring it up in solid state to the surface, and then you process it and get the uranium out of it. A pit mine, which became practical in the 1920s when people started having enough excavation equipment that could do that sort of thing economically, you simply dig, and you may just discard the overburden over here until you get to the high-paying stuff. You're not dealing with trenching and shoring and sending people down into the mine and having to keep them safe one way or another. So there are lots of advantages to open pit mines. You do tend to be left with an open pit afterward, which is unsightly and dangerous in many cases. So there are drawbacks to that. And so in both of these forms of mining, you're moving the stuff in solid state. You're crushing the ore, you're moving it to the surface somewhere, you're taking it to a mill. In recent decades, there has been an alternative method that has a lot of promise called in situ leaching, where you skip the whole moving the solid state stuff, and you instead focus on extracting it in a liquid phase. And you can, in the case of uranium in particular, you can rely on uranium's bizarre geochemistry to help you. So if you inject an oxidizing, carbonate-rich liquid into the subsurface that is selective for uranium, the carbonate will dissolve uranium and not many other things, and then that pregnant liquor can be extracted at an extraction well, and hopefully you've set up your hydrology such that this uranium-rich liquid isn't just kind of floating free off into the aquifer. This is generally not potable water anyway, since it has a uranium deposit in it. So, but you still want to watch out hydrologic control. You don't want this to leak upward into actual drinking water resources. And that sort of thing, but those are at least potentially solvable engineering problems. So not every system is susceptible to this, but where it is feasible, it has a lot of advantages. So instead of hauling solids out of the ground and processing them, you can just haul the liquor directly out of the ground. So, and in this case, so here's a very schematic overview of what happens after you've mined the uranium. In the in situ leaching, you get to skip the whole top of this diagram, and that's a great thing, because up here, all right, I have used my equipment, I've burnt carbon, to haul the stuff out of the ground. I've crushed it, I've ground it, and I've leached it. and whatever I leach it with, which is true for metals across the board. But most hydrometallurgic processes depend on really unpleasant chemicals. So we'll talk about one of those examples in a second, but strong acids, things like that. So you're left with tailings, and you're left with the leftover liquor, and you generally put those in a pile off to the side somewhere. And then you concentrate on the liquor that's got the good stuff in it. It's got the uranium. Probably you reduce the uranium, precipitate it out of solution. You wind up with something called yellow cake, which is actually a mixed oxide. It has both uranium-4 and uranium-6 in it. And that is the commercial concentrate that is then sent for fuel fabrication or weapons manufacture or whatever its destiny is. So the fact that in situ leaching skips this whole leaching and making a big pile of tailings over to the side means that it's got serious advantages over conventional mining. Okay, so very few historical examples of both mining and milling. So in central Wyoming, Wyoming is a big uranium mining state and has been since, actually before this deposit was discovered. This was not the first uranium deposit discovered in Wyoming. But a man named Neil McNeese started the Lucky Mac mine, and that started this district in motion. And again, the history is that a lot of small mines were opened here, there, and everywhere across this deposit. These are Paleochannel deposits from the early Cenozoic. They have organic material in them. There are volcanic deposits on top of them. There are Proterozoic granitoids nearby. Either or both of those supplied the uranium. It migrated into these channels, and in certain spots where there was a lot of organic matter, it gets stopped, chemically precipitated, and that's the source of the economic mineralization. So this is a fairly sizable deposit. It hasn't been worked significantly since the early 80s when the market crashed. It hasn't been worked, I think, at all since the early 90s. Uranium is an intermediate price metal, so even when we're talking about millions of pounds, we're talking about pounds. Just like if people talk about gold, they talk about how many ounces, hundreds of thousands or millions of ounces of gold have been extracted from a given district, even though we could express it in tons if we wanted to. It's just a convention for different metals. And then once that stuff was mined, it needed to be milled somewhere. So this mill only operated for about 5 years early in the history of the district. This is Riverton, Wyoming, which is 50 or 80 miles to the northwest of the Gas Hills. And so it's another great American story. It's the boundary of an Indian reservation. So despite all of the documents and so forth saying that the Arapaho could keep this land in perpetuity, they pushed somebody off of his 20 acres here next to the railroad and built a uranium mill on top of his land. So he and his animals had to go elsewhere, and they built a mill, and they built a large pile of radioactive tailings, mildly radioactive tailings. We got most of the good stuff, but it was nevertheless, it sat there for much longer than the mill was in operation. The tribes finally negotiated with the Department of Energy to have this material removed and sent actually back to the Gas Hills, I believe is where most of it went. But to this day, especially during flood events along the Little Wind River and the Wind River, monitoring wells will still reveal the presence of significant amounts of uranium in the groundwater. It's not constant, but it is intermittent, so it must be there somewhere. And when you joggle the hydrology a little bit, it reappears. So that's kind of an ordinary consequence of uranium mining. An extraordinary consequence of uranium mining happened here in New Mexico. So if you think of nuclear disasters in 1979, you typically think of 3 Mile Island. You don't typically think of Church Rock, even though Church Rock did technically release more radioactive material than 3 Mile Island did. But it happened out here on the Navajo reservation, and there's just not that many people, right? But nevertheless, it was a nasty, nasty piece of business. So there was a tailings dam holding quite a bit of tailings and spent liquor, including a bunch of fluid that was less than pH 2. Yeah, that's pretty unpleasant. So about 93, 4, 5, depending on your source, 90-some million gallons of this pH 2 stuff, and 1,100 tons of tailings broke out of this dam, which itself was probably mostly a pile of tailings, And it roared down this arroyo into this river, and it's July in New Mexico, so most of the flow in this river for at least a short period of time was radioactive tailings liquor. So it's, again, there was probably a ton of uranium, all told, in that stuff. That's a lot. That's quite a lot. And it's not altogether clear whether the entire extent of this release was ever completely clarified, pinned down. Arguments about that to this day. And in fact, there's a Superfund site here at the source area where, at the source area, in that local area, they still haven't got the uranium plume under control. It is still expanding, albeit slowly. All right, so far, that's all of the stuff that leads up to taking the uranium and using it for something. So we go to all of this trouble in order to get energy out of it. Occasionally catastrophic releases of energy that we call nuclear weapons, but hopefully mostly for electrical power, which is beneficial for people. So broadly speaking, very broadly speaking, and there are a lot of different details, but different types of reactors will affect this. This is actually taken from the Japanese nuclear agency or the Japanese consortium of power plants, I forget which. I didn't credit this figure, I apologize. But broadly speaking, what happens is if you have a conventional reactor, you enrich the uranium. So naturally, on the current Earth, U-235 is tenths of a weight percent. You need it to be percent in order to put it into a conventional light water reactor. You then allow that to react for a while. You still have some uranium-235 left. You have neutron bombarded a lot of the U-238. You've built yourself a chain of transuranics. So you've got neptunium, plutonium, americium, curium, maybe even a little californium. So all those, well, they have a variety of half-lives. Some of them have very long half-lives. You've also got a bunch of fission products, and nearly all of them have relatively short half-lives. Now, short maybe 80 years, but not, as a neptunium-237 is something like 1.5 million or something like that. So the transuranics have the really long lifetimes and are problematic for that reason. So, that was not what I wanted to do. Okay. So once you've got the spent fuel, you have options. We always have options. So you could reprocess the fuel, which means extract some more useful value out of it. It is a messy process. It's basically another hydrometallurgic process is the current technology. We can extract the uranium, we can extract the plutonium. Some of the plutonium is fissile, and we can use the fuel again and get more good out of it. Eventually, current thinking is definitely that we're going to put some waste product, some spent fuel at the end of the process somewhere. And of course in the United States, I believe it is still a matter of statute that we're supposed to put it at Yucca Mountain, even though Nevada has stopped that permanently, and we're at an impasse until Congress actually manages to pass legislation and try to do something else with it. So we can take Yucca Mountain as an example of the kind of thinking that needs to go into a repository, and every repository, every potential repository would have pluses and minuses. Yucca Mountain would have the big plus that it is in the middle of nowhere. I mean, it's 80 miles from Las Vegas. It's not absolutely the middle of nowhere. But it's a ways. It's a considerable distance. It doesn't rain much there. These are pros. It is in the middle of this volcanic pile of tuff, which is volcanic ash that's turned to clay. That's fairly water impermeable. That's good. It is, of course, cracked because every geologic formation is. It has faults nearby. That's not so great. There could be more volcanic activity there in the future. That's not so great. I mean, you got to pick somewhere, and you also have to get it somewhere. So you could literally. One thought is that you could literally take the waste to Cigar Lake, which is in northern Saskatchewan, ain't close to nobody, and it is in a geologic environment where it actually would be more immobilized there because the chemistry is set up correctly. There's nothing chemically speaking about Yucca Mountain that's advantageous, which is fine-ish. You don't need chemistry working for you when you've got this much physics working for you. It's okay, but nothing's perfect. Nothing's going to be perfect. What are we going to do with this stuff? So just to wrap up just a minute or two, of course, why, especially in current debate, why would anybody be in favor of nuclear power? because the intrinsic reaction getting you the power doesn't involve generating carbon dioxide. Building the plant definitely demands carbon dioxide. Mining the uranium and transporting it places consumes carbon dioxide, but you incur all those costs when you're moving gas and coal and so forth anyway. So it's obviously a win from that perspective. It's a little sad that people who consider themselves environmentalists, by and large, are just, they're almost kind of knee-jerk opposed to nuclear power. Does it have problems? Yes, it does. Are there things that would need to be done in order to make it safe, better than we've done in the past? Yeah, there would need to be. Can we do those? Probably. We probably can. Nuclear accidents, do happen. Many of them can be avoided. Human error can't always be eliminated, but it can be reduced. The big problem actually right now is that we don't seem to be learning how to build nuclear power plants in terms of the engineering, the costs. They're massive, massive cost overruns. The two that are being built in the United States today, I think of a planned 8 or 9 billion, they're going to spend 30 billion on them. That's problematic. So there are new generations of fission reactors that are being thought through. I'm not prepared to talk about them in detail. I would love to hear your discussion about them if you know about those or interested in those. And then a final thought, fission energy was always kind of in some sense thought of as a stopgap until we get fusion online. And fusion has taken a long time. Do we need one more generation of fission reactors before fusion finally comes online? Maybe. Or are we going to be able to skate by with fossil fuels or whatever renewables we can get to work? Food for thought. So I appreciate your attention, and with that, let's have some questions. Thank you.